Welcome back everyone. In this lecture I will continue Cartan's criterion for semisimplicity. So we already saw Cartan's first criterion for solubility in terms of the trace conditions. So because this trace condition is actually going to play big role, so we will introduce what is called this killing form in terms of this trace, okay, which will play important role later what comes for next. So let me just define what is called this killing form. So this can be actually defined any 5-dimensional complex Lie algebra. So there is no restriction on the complex Lie algebra. So we take G to be complex Lie algebra. So that means Lie algebra defined over complex numbers. So then the killing form is actually, so this is defined on G, okay. So it is actually a symmetric bilinear form defined by the following condition. So this is denoted by kappa, which is defined from G cross G to complex numbers. So this is defined to be kappa of x comma y is given by the trace of add x composition add y for all x, y and g. So this is how it is defined. So note that, so by definition, since trace being linear and add x being linear, you can see that this kappa is actually a bilinear form. So the kappa is a bilinear form on this G, okay. So not only that, this is also a symmetric form, is symmetric because trace of AB is being trace of BA gives us kappa being symmetric. So now there is one more important property that actually one can get it from the trace identity. So recall that trace of A times bracket BC is same as trace of bracket AB times C. So now if we just write this identity here in terms of kappa, so then what we get? So we get kappa of bracket xy times z is actually equal to trace of add x add y. So this is bracket add x bracket y times this z add z composition add z. So then we get exactly equal to trace of add x add y composition add z, okay. So now if you just use this identity, then you can see that this is same as trace of add x composition add y add z. So that means this trace identity actually gives some condition on this kappa. So this kappa of x comma the bracket y z is same as the kappa of bracket x y comma z. So this identity is actually called associativity of this killing form. So the kappa of bracket x y z is same as kappa of x comma bracket y z, and this is true for all x y z in G. So this is called associativity. So this associativity is actually very important property of the killing form, because this associativity can be used to prove that the radical of this killing form is actually an ideal inside G. Not only that, if we take any ideal, the perpendicular of that ideal is also ideal inside G. Those things can be proved using this associativity. So, now once we have this killing form, it is not very hard to rewrite the Cartan's first criterion. So, in terms of this killing form, so we say complex Lie algebra G is solvable, the complex Lie algebra G is solvable if and only if we take the kappa of x y is 0 for all x in G and y is in G dash. Okay. So, this is very strong condition for being solvable. So, let us see in terms of radical of the killing form what this means. Okay. So, that way actually we will get some more insight about this criterion. So, what is the radical of the killing form? So, the radical of the killing form, okay, here is the definition. The radical of the killing form or kappa. So, it is by definition, okay, we denote it by small rad of kappa. So, this is those x in G such that this kappa is actually kills this x, okay, for all y. So, the kappa of x y is 0 for all y in G. So, such subspace. So, this is definitely a subspace of your G. Okay, you can see that. So, this is indeed ideal inside G. So, here is the claim, radical of this kappa is indeed ideal inside G. So, now what is this Cartan's criterion? First criterion says about solvability. So, this says that the radical of this kappa contains the derived algebra G dash. So, that is what it says. So, this is very strong constraint on this killing form. The radical is actually very you can see that this is not a good subspace, okay, but solvability is actually equivalent saying that this radical is indeed contains large portion of your G, which is the derived algebra. Now, let us see why this radical is actually being ideal. Okay. So, to prove that radical is being ideal, let x is in the radical and y is in G. So, then we need to check the bracket x y is in the radical. So, let us compute the bracket x y. So, now to say that this bracket x y is in the radical. So, we have to compute how it is actually the value of the trace with this bracket x y and z. So, that is the kappa of bracket x y comma z. Now, using this the associativity of kappa, you can see that the kappa of bracket x y comma z is same as the bracket. So, maybe we will switch this bracket y x comma z. Okay, maybe we do not need to switch, we will just keep it as it is. So, the kappa of bracket x y comma z is same as bracket kappa of x bracket y z. So, now since this x is in the radical of kappa, you can see that kappa of x comma w is 0 for all w in G. So, since this y and z both are in G, so the bracket y z is in G. So, that implies this kappa of x comma this w is actually 0. So, that implies kappa of bracket x y comma z is 0 for all z in G. So, that implies the bracket x y is again in the radical of kappa. So, this proves that the radical of kappa is actually indeed ideal inside G. So, this is somewhat important ideal. So, solubility actually equivalent to saying that, so this G dash is actually contained in the radical of kappa. Okay. We will soon see that for semisimplicity it is completely the opposite thing. For semisimplicity, so this radical should be actually 0. So, it is actually as small as possible, which is 0. So, now let us compute how this killing form behaves with respect to some ideal. So, you start with ideal inside G. Okay. So, now since I being Lie algebra, one can talk about killing form with respect to I. Okay. So, which we call it kappa I. So, which is the killing form defined from I cross I to complex numbers. So, this is the killing form of I. So, now we have killing form defined from G cross G to C. So, we can also restrict this killing form to I cross I. So, we have this another map which is again symmetric bilinear map from I cross I to I. So, what is the connection between these two maps? So, it is easy to see that these two maps must be same. So, kappa defined on I should be same as kappa restricted to I cross I. Okay. So, this must be true for any ideal I in G. So, how one can prove this? It is again easy to prove. So, you start with the basis of I. Okay. So, start with a basis of I and extend this to G. So, then you can see that for any x in I, so this add x, this is actually going to map G into I. Okay. So, in particularly if you look at this add x with respect to the basis that we have constructed. Okay. So, this is the basis that I am talking about B. So, then you can see that this matrix of this add x with respect to this B will look like this block matrices. So, some A x 0 and B x 0. So, this A x is the matrix of add x restricted to I. Okay. This A x is the matrix of add x restricted to I. So, this is something very easy to see. So, in particularly if we actually compute the composition, okay, if we take y inside I, so then if we compute add x composition, add y, then the matrix of this with respect to the same basis, it will look like the product of these two matrices A x times A y and then here 0 0 and whatever is there, this is going to be A x times B y. So, which we do not care. Okay. So, this is how the matrix will look like. So, in particularly this A x time A y is the matrix of this add x composition add y restricted to I. So, in particularly if you compute the kappa of x y, so which is the restriction of kappa of I to I cross I, then you can see that this is same as trace of A x A y, which is actually the definition of kappa I of x comma y. So, that proves the kappa restricted to I cross I is same as kappa I. Okay. So, this proves that this killing form with respect to ideals behaves very well. Okay. So, now we are actually indeed ready to actually state the Cartan's second criterion for semisimplicity. So, we will actually prove this criterion using some basic informations about the killing form. again we will actually need the first criterion to in order to prove this second criterion. So, let us actually first state the criterion and then we will see. So, here are the following statements actually equivalent. Okay, the following statements are all equivalent. So, here is the second criterion, which again we call it theorem. So, what it says, so this is about again one can restrict it to complex numbers. So, let G be a complex Lie algebra. So, then G is semi-simple. So, by definition the radical of this G must be 0. So, that is the maximal soluble ideal must be 0. So, that is the first condition. So, now in terms of this killing form, the killing form of this G must be non-degenerate. So, that means the radical of this killing form must be 0. So, the killing form is non-degenerate. So, this is by definition radical of this kappa being 0. Okay. So, here the by definition radical of G being 0. Okay. So, the third condition is that G has no non-zero ideal, non-zero abelian ideal. So, this is more or less equivalent to the definition. And the fourth condition is again we can rewrite this non-zero abelian ideal being non-zero soluble ideal. G has no non-zero soluble ideal inside G. Okay. So, we already proved that 3 and 4 are equivalent. So, we will just only prove first 3 are equivalent. So, how one proves actually 1 implies 2. So, you first assume that G is semi-simple, that means the maximal soluble ideal that is actually 0. Now, look at this radical of this killing form K. Okay. So, 1 implies 2. So, look at this radical of K. So, by definition this is those x in G such that the killing form kappa of x y is 0 for all y in G. Okay. So, note that in particularly if we take any x y from this radical of kappa, so then kappa of x y is 0. So, then using this first criterion of first Cartan's criterion of solubility, we can conclude that radical of kappa must be actually soluble. Okay. So, note that kappa of x y is 0 for all x y in radical of kappa. Okay. So, that implies radical of kappa must be soluble. Okay. But we already checked this is an ideal. So, this is soluble plus ideal. So, this is actually contained inside radical of G. But G is being semi-simple, that implies that radical of G is 0. So, that implies that this radical of kappa is also 0. So, that means kappa is non-degenerate, kappa is non-degenerate. Okay. So, now what is about 2 implies 3. So, we assume that kappa is actually non-degenerate, that means radical of kappa is 0. Then we want to prove that G has no non-zero abelian ideal. So, let us assume that G has some non-zero abelian ideal. So, there is this I which is non-zero abelian ideal inside your G. So, then you can see that if we take these maps, let us say A is from I and then X is from G, then look at this add A, composition, add X, composition, add A. So, add A is going to map G to I, and then X is going to map I to I. So, then A will map I to 0. So, that means this add A, add X, composition add A, this map G to 0. So, in particularly if we take this add X composition add A, so this square will be 0 on G. Okay. So, in particularly this add X composition add A, this is a nilpotent operator on G. So, kappa of A x is 0 for all x in G. Okay. So, this implies this I is actually contained in radical of kappa, but radical of kappa is given to be 0, that is the condition 2. So, that says that this I must be 0, okay, which is a contradiction because we started with I being non-zero. So, that proves that 2 implies 3. Okay. Now, for 3 implies 4, so that is obvious because if G has a non-zero solvable ideal, then look at this derived series. Okay. So, then the last but first non-zero term, okay, that will be actually abelian ideal, that we have seen already. So, again like if it has no non-zero solvable ideal, then that would imply that there is no actually maximal solvable ideal. So, all these statements are being equivalent is proved using Cartan's first criterion. So, this K being non-degenerate, this is very important criterion for semi-simplicity. So, let us see what are all the consequence of this K being actually non-degenerate. So, given ideal inside G, so one can talk about what is called I perp. So, this is the perpendicular of I, okay, perp of I. So, what is this by definition? So, this is those x in G such that the kappa of x comma y is 0 for all y in I. Okay. So, those elements that are actually orthogonal to these all elements of capital I, that is called I perp. So, it is easy to see that I perp is always subspace of G. Okay. So, this is a subspace. So, one can using the associativity, one can prove that I perp is indeed ideal inside G. So, let us check that. So, let x is in I perp and then y is in G. So, we need to claim that the bracket x y, so that is inside your I perp. So, how one can prove this is inside I perp? So, let us do the computation. So, if we compute kappa of the bracket x y and then you take some z from your I, okay. So, then we need to show this kappa of bracket x y comma z, that must be 0. So, that is the definition of bracket x y being in I perp. So, then if you take for z in I, the kappa of bracket x y z is equal to kappa of x comma bracket y z using the associativity. So, then you can see that this bracket y z. So, since y is coming from G, z is coming from I. So, this is coming from capital I. Since x is coming from I perp, you can see that the kappa of x comma bracket y z. So, this term must be 0. So, that implies bracket kappa of bracket x y comma z is 0 for all z is in I. So, that implies that the bracket x y is in I perp. So, this proves I perp is indeed ideal inside G. Okay. So, now if we have this semi-simple Lie algebra, then we know that this killing form actually being non-degenerate. So, because it is actually non-degenerate, so that would immediately imply that, so if G is semi-simple, so then and I is an ideal inside G, So, since K being non-degenerate, we immediately have the dimension of I plus dimension of I perp is being equal to dimension of G. Okay. So, this is actually immediate from this K being non-degenerate. Now, not only this, you can actually see that if you look at what will happen to the intersection. Okay. So, now look at I intersection I perp and then see what happens. Okay. So, this is nothing but those elements that are common to both I and I intersection I and I perp. But if I take any x comma y in this I intersection I perp, so we can see that kappa of x comma y must be 0, because x is coming from I and y is coming from I perp. So, now if we use this Cartan's first criterion, okay, the first criterion says Cartan's first criterion says I intersection I perp must be solvable. So, since intersection of two ideals must be ideal, so this implies I intersection I perp is a solvable ideal inside your G. Now, if you assume G is semi-simple, then you can see that there is no non-zero solvable ideal. So, that forces that I intersection I perp is 0. So, this proves G is indeed equal to I direct sum I perp. Okay. So, because the dimension of I and the dimension of I perp, so they add up to dimension of G, and I intersection I perp is being 0, that would imply that G must be equal to I direct sum I perp. So, indeed what we proved, so we summarize this is as corollary. If I is ideal, non-zero ideal inside your G and G is semi-simple, then G can be written as I direct sum I perp. Not only that, I must be actually semi-simple. Moreover, I must be semi-simple. Why? Because if we take G modulo I perp, so then that is isomorphic to I. So, now if you look at the radical of this G modulo I perp, you can see that, so that must be 0, because radical of G is 0. So, that would imply that I must be semi-simple. Okay. So, now using this corollary, we can actually decompose any semi-simple Lie algebra into simple Lie algebras. So, that I will actually state it as theorem. Okay. So, now one can use induction and then write any semi-simple Lie algebra as direct sum of simple ideals. And if we think about it, this is also going to give us one more characterization for semi-simple Lie algebras. So, you take G be a complex Lie algebra. So, then G is semi-simple if and only if there are simple ideals or simple algebras, okay, G1 etc. Gr such that G is equal to G1 direct sum etc. direct sum Gr. So, one way is actually clear. So, this is just by induction on the dimension and kappa being non-degenerate. So, if you start with G, if it does not have any proper non-zero ideal, then it must be simple. So, in that case we just leave it, otherwise you choose non-zero proper ideal, then you write G as I direct sum I perp using the earlier result. Now, using induction on I, we can actually write G as direct sum of simple ideals. So, that is obvious. So, now we will prove the other way. So, if you actually write G as G1 direct sum etc. direct sum GR, where GIs are simple ideals. So, then we want to claim that G must be actually semi-simple. So, to prove G is semi-simple, so we will actually prove that directly the radical of G must be 0, or otherwise we can also take some solvable ideal and then try to prove that must be 0. So, let us try to prove that the radical is actually 0. So, let us call the radical of G to be I. So, we claim that radical of G must be 0. So, note that this I bracket with G I. So, this is if it is non-zero. So, in any case whether it is 0 or not does not matter, this has to be subset of I intersection G I, okay, because G I being simple ideals. So, the bracket I with the G I must lie inside both capital I as well as G I. So, that would imply that this is actually subset of I intersection G I. So, since I is solvable ideal, so this is also must be solvable. Okay. So, this bracket being solvable. So, not only bracket, the intersection is also solvable, I intersection G I, because I is being solvable. So, that implies since G I they are all simple ideals, so that makes I intersection G I being 0. So, that implies the bracket I with G I, that is also 0. So, now note that I bracket with G should be equal to summation the bracket I with G I, but each one of them 0. So, that will imply that this bracket I with G is 0. So, that makes I is subset of the center of G. Okay. Now, since G is G1 direct sum etc. direct sum GR, that implies the center of G must be just sum of the centers Z G1 direct sum etc. Z GR. Since each GI is actually simple ideal, so that implies that Z of GI is 0 for all I, and that tells us that center of G is 0. So, that will imply that I is 0 because I is subset of center of G. So, this proves that I, which is radical of G, must be 0. Okay. So, that proves that G is semi-simple. So, this is a very important criterion, because it says that the bracket if we know G is semi-simple, then G can be written as a direct sum of simple ideals. Now, as an immediate corollary, one can easily get the following. So, since actually this G can be written as a direct sum of simple ideals, so we can see that so the derived algebra of G. So, G bracket G, that must be G if G is actually semi-simple. Why? Because we know this is true for simple ideals. Okay. If G is I is simple Lie algebra, so then we know that the bracket GI is non-zero and it is ideal inside GI. So, that says the bracket GI must be equal to GI. So, now since G being semi-simple, you can write G as G1 direct sum etc. direct sum GR with the GI being simple ideals. So, you can see that the bracket GG will be summation the bracket GI. So, which is same as summation GI which is G. Okay. So, this proves immediately the bracket of GG, which is the derived algebra, is equal to G. So, now as I said, if I is an ideal of G, G is semi-simple, then the quotient of that I is also the quotient G mod I is also semi-simple. Okay, that is also immediate corollary. If I is an ideal inside G and G is semi-simple, so then G mod I is also semi-simple. So, semi-simple Lie algebras are also well behaved with respect to quotient. Okay, this is very important property of this semi-simple Lie algebras. Okay, so let me just recall Cartan's second criterion and their consequences. After that, I will stop. Okay, so what we proved that. So this is the Cartan's second criterion. So G is semi-simple. You take G being finite dimensional complex Lie algebra, then G is semi-simple if and only if the radical of this the killing form, that is 0. So it's a very, very important criterion for semi-simplicity. So this is for the criterion for semi-simplicity. We used solubility criterion to prove this. So what is solubility criterion? G is soluble if and only if the radical of kappa is actually contains the derived algebra G dash. So these two are two extreme cases you can see in terms of this killing form. Okay. So I will stop here. I will actually continue with derivations of semi-simple Lie algebras in the next class. So we will use whatever results that we have learned so far about this Jordan-Chevalier decomposition and so on, and then use that in order to understand what is called this abstract Jordan decomposition for semi-simple Lie algebras. Thank you. I will stop here.